Okay, folks, welcome to Module 2. We're going to be talking about programming in C++ today and structuring our programs. But first, a little pre-class warm-up to figure out which language inspires C++. So go ahead and pause, hit spacebar if you like, and then we will continue here. And this is not a trick question, so I'll reveal the answer that, well, C++ was inspired by the C language. So as you would have guessed, many of you have seen C in a systems or equivalent course. The plus after C is a sort of play on the increment operator, so it's sort of a fun way to introduce the language as an improvement upon the C language. And early on, C++ was just known as a C with classes language. So when it was first being developed in the 70s, that was the main feature, that this sort of some of these object-oriented features were added. So those are the features I want to talk about today. So with that, let's go ahead and dive in. Okay, so before we dive in though, last class what we did, a little review, is we got an introduction to the course. Please remember to look over the syllabus and just make sure you're clear on how the course is going to be run. Again, reminder that Monday we'll meet at the class time, but it'll be a quick review of this lecture and then office hours for questions. Wednesday will be a quick review of the lab to start and then questions on the lab. So I introduced the C++ language last week in a sort of blitz, if you will, a very quick round of the features in the language, including features like just how to write hello, namespaces, pointers, a review on that if you needed. Again, hopefully you got that from the lab. The lab, again, which will be due next Wednesday. I talked about how we think about a compiled language. So C++, again, is compiled. So we think about what happens at compile time in ways we can look at our code at compile time versus when our code is actually running. We looked at namespaces, a way to organize our code. We're going to do some more hands-on examples today with that. And then we looked at classes briefly. So I'm going to do more stuff with classes today to show some working examples. And then finally, we looked at Git and GitHub, and you did some refactoring or working on it still in your lab, getting it set up with Git. So the prompt for today, to sort of motivate this lecture, is that you're a student. Well, you are if you're watching this class, and you're getting ready for your nth job, whether it's your first one, your 10th one, because you've been working a long time, and you're reviewing applications. But you consistently see C++ in the job description for the set of skills. And often you'll see this, you can do this as an exercise, but you'll see C++ programming experience needed, or N years of programming experience, C++ is preferred. So, you decide after seeing enough of these listings that you want to take the first step of letting your employers know that you're learning C++ by completing some skills and earning certificates that you shared on LinkedIn. So again, that's from your first lab. I want you knocking those out so you can show them off to the world. But then you decide the next best way to ramp up your skills is to actually structure a project on GitHub. And this is, no secret, I hope, but employers like to see projects on GitHub and code that you've actually written and thought about and developed. So that's, again, stuff we want to be working on, again, putting up some real code by the end of this course. Okay, but we're going to get some C++ up and running today. So let's dive in. So a little bit on C++, the language. It's really a multi-paradigm language, meaning you can write C++ code in a number of ways. You can sort of write it procedurally. So for those of you, again, remembering your C programming, whether from systems or another class at another university, you have functions, you have pointers, you have structs. You can write C++ and only use those features. That's fine. In fact, you can write good code that way if that's all you need. But you can, sort of restrict yourself to procedural way. But if you need it, C++ provides object-oriented features. This is the way most people, I would say, use C++, using things like classes, inheritance, virtual functions, these kind of things we'll talk about more of. But certainly, classes and objects when we think about C++. And then more recently, you can write C++ in a functional way. So the modern C++ that we're doing, we'll look at a few cases where you can use lambdas, really think about making your data immutable. So this is one other programming paradigm. And there might be others, you can write it in a structured way and so on, okay? But the predominant way, again, as mentioned, that I've seen C++ used is as an object-oriented language. So I want to show you some of those features today. Okay, so with those paradigms, though, just to understand what they are, a procedural programming style is, again, to sort of create a program one line at a time. Again, your building blocks are functions to build, bigger programs. So here's an example of a procedural style program. We've got some functions defined here before you're going to use them, a main, your entry point to the program, and then you're making various function calls here. Okay, that's the basic idea with procedural programming. Okay, so question for the audience, what happens to this source code as it grows very large? And I want you to think about, having a code base where you can only use functions, and you've got 1 million lines of code to maintain. So go ahead and pause the video, think about it. What do you think happens, to the source code as it grows very large? And you can give me a variety of answers. And if you've paused to think about it a little bit, some of the ones that we might come up with is, there's lots of functions. You have them, many functions. It can be very hard to maintain, this code. I'm, again, thinking about millions of lines of code. Yeah, some projects do it, like the Linux operating system, but, those are very hard to maintain and have, hundreds of developers very closely, curating things, all the way up to the top of what code actually gets in. So, furthermore, just having projects without proper abstractions that help us, separate our project into different files and so on, makes our code generally harder to scale, okay? So we want to continue from this example and sort of transform it in a more object-oriented way, okay? And we're going to build a little small screensaver just at the end, just to have a sort of pragmatic example of how to build something or a piece of software and separate it into smaller components. Okay, so object-oriented programming in C++. Let's talk about that a little bit. So we have this code here with some functions. This was just some quick pseudocode that I've written up. But I want to start to analyze different ways of how we can just make this code better. I've got a few freestanding functions here for creating a window, setting the frame rate of that window, how often it'll refresh, maybe a function to display some graphics to the user. So what can we do to make our code more object-oriented? Okay. So one thing we can start out with is to actually separate out our code into more logical units. Okay, so these 3 functions that I listed had something to do with a window, for instance. So we can group them together here by putting them in the same namespace. So I'm going to call this namespace SF. It'll make sense why I do that by the end of the lecture. But they're all just grouped together. So window is part of this SF namespace, set frame limit is part of SF, and display graphics is also part of SF. Okay, so now if you're going to call these functions, they're all SF : window, SF : set frame rate limit, and so on. Okay, so this namespace, what it's really doing is it's providing the scope for these functions. Okay, so window is in the scope of the SF namespace. They're all grouped together. And this helps. This is a hint to you as a programmer if you're using these functions that maybe they have a common functionality, or these are from the same developer who made all these functions, or they're part of the Windows module as opposed to a group of functions that are with the audio group of functions. Okay, so it's just one way to organize your code. But the problem here with only using namespaces is that, what if I want to create multiple windows here? Okay, I still have this function to just sort of create one window here. And again, if I only have one window, maybe I want them to have different frame rates and display different graphics on them because you've got an application with multiple windows running, like an internet web browser or something. So we need to reorganize this function a little bit. We need to refactor it in a way. We still like this namespace abstraction. They're still logically grouped based off the functionality of what these functions do, but we want to group them together, or at least be able to be more flexible of what these functions offer. So one thing that we can do, again, if we already know the C language from systems or another similar language where you learn something C style, is you can create a struct which will hold all the information about a window. So here's a struct here. I'm just going to call it window object, and it's going to represent a window, like an actual screen here that I have a width, a height, a title, and the limit is how often it refreshes. So then I can create as many windows as I want by just allocating memory for these structures here. So for brevity, I've just included window 1, window 2 here. Pointers to those windows, maybe they get initialized somewhere else. But now we can see window 1 and window 2. Okay, and then I can use them in my function or functions as much as I want by just passing in a sort of handle to which window I'm modifying. So this in the namespace SF, window, I'm using window 1. So you'll notice in all these functions I've added window object underscore t, a pointer to that window, which is modifying data for each of these functions. Okay, so this is one strategy, and we usually call these handles. They can either be the actual object themselves, or a little cheaper ways to make these an integer for a specific window. So this is one strategy. Okay. Question though for the audience, and again you can pause the video and think about this, but what might be some problems with this approach? If you're joining back with us, some problems are, well, the interface here, it's a little bit tricky for the user. You as a developer have to remember which window you're working on. So you could pass in the wrong window or wrong object here. Maybe something that's not even a window, but just some address here, that happens to fit here. So that could be a problem. You may forget to free or allocate memory like I've done here. I haven't explicitly done it here. And you need to remember to free any other memory allocated in these functions. Maybe they're allocating memory here. We lose track of it or whatever. It's just a little bit clunky. Sometimes this is okay. We do this in C programming all the time. We sort of pass a handle or an object as the first parameter, but it's still clunky. It can be error prone. We again probably want a better abstraction on top of this, right? So, to be fair, there are some solutions to these problems, right? Of just being careful, or writing separate constructor functions that only allocate or deallocate memory, and then none of these do. But you really have to follow a strict or be very disciplined programmer to make this work. C programmers have made it work, so it is possible, but we can do better, right, than just saying, hey, we have to test more or be very careful. Okay, so again, the point is though that all these functions are related. They're accessing the data in this struct. So it is really one sort of logical unit or group. And this is where object-oriented programming comes in, where we just want to think about this whole set of functions and data as one object. Okay, so that's where we're diving in for the different programming paradigms and then how to structure a C++ project. That's what today is all about. Okay, so we're going to turn what's on the left here, what I just showed in the last slide, to this C++ code. And I've sort of just done this for you, but I'll explain the different parts. But you can see the namespace still remains, but we have this class keyword, and then all the functions are embedded within this class here between these two curly braces. Okay, the curly braces at line 5 and 24. And all the data from our struct is in this class. Okay, let's look at the pieces again, just one at a time. So just breaking this down a little bit further, again, a class in C++, it's just a user-defined type that we create, right? We want some representation of a window in our program. Okay, so now we have this custom data type where we can instantiate windows. With classes, again, we keep together the behavior and the data. And this is really convenient for us as programmers to think of the behaviors here, which are the functions, which do the work, which are here. And some of these functions, have specific roles that they play. like the constructor, which is always named the same thing as the data type, which is first called when you create an object of this type here. Okay, so here I'm creating a window 1, and here's the function that's called when I create a window. Okay, so it's going to allocate memory, set the width and the height, and so on. Okay, and then I can have any other functions here. And then the data that's associated, so sort of the storage in the class, whether it's variables or other container data structure, is in the class as well. Okay, the width of the window, height, the title, limit, anything else that we can think of. And then we have this additional power that's really nice with C++ classes, in that we can say what's public and private. So to tell us what's exposed outside of the class. And this is important just for the user of your API, or of this class really. So they know they can call anything under the public function, this window, this set frame inlet, display graphic, but you have this sort of guarantee, or at least it makes it much harder to access width, height, title, limit, and so on. You want the user of this class, whether it's you or somebody else, to only use these functions. Okay, so it's a nice sort of defensive programming style in that way. Okay, and then again, since we're taking this as object-oriented programming, it has the word object in object-oriented programming, we can think about creating these windows as separate instances. So that's down here in the bottom right corner, where I'm creating each of these windows, window 1 and window 2, and they're completely separate instances of the type window here. Okay. And this more closely mirrors how we think about things in real world, right? If you've got chairs in the real world, you can think of them as separate chairs. If you see cars on the street, they're separate cars with their own sort of attributes of, how fast they drive, how much, gas or electric you have left in the car, how many wheels it has, and so on. Okay, so those are all the different properties you can set up for each separate instance of an object. Now, how it's working behind the scenes, just a little insight, is, a compiler is probably converting your class into what we saw before. So, this class, in a sense, C++, when you get down to the primitives, it's just, what we saw before, a window here, and then there will be a pointer here. The specific pointer is the this pointer. So again, if I go back a few slides, on this side, you have this implicit sort of pointer. It's being stored somewhere every time you create this object, and it's called the this object in C++. Okay, so I just want to make that sort of clear what's going on behind the scenes. Okay, so hopefully now, after seeing this tiny example, if you've never seen it before, you can see, separating things into classes and functions just makes things a little bit more easier for us. It's a little bit more organized if I know everything that has to do with a window is in this class here. Okay, so with that in mind, I want to talk a little bit more just about how to organize our software projects. Because it's great if we can create classes, but how do we sort of organize things to effectively write C++ code? Okay, so this is about the C++ project structure. So in C++, we typically organize our projects in two kinds of files. There's the CPP source code file. Sometimes it has different abbreviations, but that's what contains the behaviors of the code, all the functions, how the different work's done. And then there's something we call header files, and they end in .hpp or sometimes .h or .hxx. And that contains the declarations of our code. And that is where your interface is defined. Okay, so what functionality that you do have, but how to actually do it, again, is in the CPP file here. Okay, and something else to keep in mind is that when we compile our project, we're generating in C++ what's called a binary object file. And most of the time that's just an executable, right? That's the thing you double click and run. So we have our source code, the interfaces, and then we compile our source code, and we get the executable file. Okay, so Windows users see exe, Mac users .app, Linux users .app file, or a file with no extension that you just double click on and it runs your program. We are going to talk about other object files like DLLs, shared objects, dynamic apps, other object files later on in the course. Okay, But remember, C++ is a compiled language. So one way to just organize our source code is to sort of set up this common hierarchy here where you have a source directory which contains your C++ files and an include directory which contains any of your header files, those .h or .hpp files. And then a bin directory, which is short for a binary, which contains anything that can execute. So here's sort of the hierarchy, if you will, of a project that might have some source files, maybe no header files or whatever. Okay, so we want to structure this example that we've been running with, creating a window to have 3 files in total. Just for now to keep things simple, but we're going to have a main CPP, which contains the main function, which is our entry point into any C++ program. We're going to have the window.h, which is the interface for our window functions, and the window.cpp, which is the implementation of our window functions. Okay, so this is our interface, this is our actual implementation. Okay, so here's what it looks like. And I've created the classes already, or just separated out that previous code. But here's our CPP file, here our main, here is our interface, the header file, and then a C++ file, window.cpp, with the actual definitions of each of these functions here. Okay, so let's start with the main CPP file, just explaining a little bit about how this works. And in the first code line here, line 2, we see that we're including window.h. So that's including this file here in the bottom left. And this is effectively taking this file, copying and pasting it at the start of line 2 here, and giving us this interface. Anytime we see include, that's what it's doing. It's a copy and paste operation, okay? And it's copying and pasting it if it hasn't seen that window file before, okay? So that way we know what a window is, so we know we can create one. How we create it will be defined here, okay, which we'll get to. But that's what the include line is doing. Okay, so by including window.h, we get access to this class now. We can now declare and create windows, which have been defined elsewhere. Okay, they've been declared here and defined in the C++ file. Now within the window.h file again, we have the declaration. We have the declarations, all of our functions here, okay? Again, that's in this class file. So again, they're declared here in the header file, and then we define them later in the C++ file. Typically, we just have one class per header file. So you'll just see, this one file and one class here. That's a best practice in general. It just makes it really clear that when you have the window.h included, that you get the window class here, okay? Okay, so I want to have you observe one other thing here. So we talked about this include here in the main. That's basically a copy and paste information, copy and paste operation, copying this file and pasting it here. But what we have here, again, anything that starts with a pound is sort of taken by something, taken care of the preprocessor at compile time and evaluated. So includes just a copy and paste operation, but these define symbols, what they're doing is saying, if not defined, window H, this symbol, define it, and then, bring in the rest of this code, otherwise end if. But if I were to add another include window.h here, it would have already defined this window_h symbol, so it wouldn't copy in the class a second time. And that's a good thing that protects us because we can only have this symbol defined once, right? If you've ever tried to name a variable the same thing before, you'll get a sort of error symbol already exists thing from your compiler. So that's what this is doing for. So always have header guards in your files, in your .h files specifically. That prevents this double sort of declaration here. Okay. Now we also have included our namespace here for our class. So we do that here. So this window class is part of the SF namespace. We typically do this when we write our own code because it helps us just, again, logically group functions together. So, maybe this is a library name, I could have put this in the mic namespace just to make sure that things are clear here. But the idea is we want to avoid naming collisions. So if I included some other code some other developer wrote, or later on in the project wanted to use window again because it made sense for different kind of window, I could put it in a different namespace and just avoid having that collision. Okay, so I'm going to actually again declare this type by doing SF, the namespace, : window. And the : again, this is the scope operator. This tells me the scope of this item that follows it. Okay, so window can be found in the SF namespace in this case. Okay, so moving on to our C++ file, we'll define the member functions in the class of our header file. Okay, so we're including this window.h. So if it hasn't been included before, maybe it wasn't in this file or we compiled this separately, we'll have, again, the declarations of a class for a window, and now we just need to define them. Okay, so they fall in this SF namespace, so we have to do this here. But now we can actually define the function. So the scope of where I find window or set frame rate limit is within the window class. So again, here's that scope operator. Okay, so here's the actual definitions being done. And then when I actually go to use one of these functions, if I wanted to just call it as a freestanding function, it's a static function we'll talk about, it'd be sort of SF : window : display graphics. Okay, so you can sort of interpret this as it's in the SF namespace implementing the display graphics function, which is a member function of the window class. Okay, so that's how you could read this function name, and it has all of its scope in the SF namespace, the window class. This is the function name. Okay, so it's a little bit subtle, and it might be a weird sort of explanation, but this is, again, getting into the mindset of a C++ programmer, how we sort of think about things. Again, just paying attention to the scope operator. It'll make your life a little bit easier when you're just thinking about how C++ projects are organized, or why you're not calling some function or something like that later on. Okay, so now let's actually compile and build our software. That we have this little test program that we can start working with. And in order to compile our software, we're going to build it. That means building out that binary file. So we need some sort of build system to do this. You're going to work with this a little bit in your lab to see a build system called CMake, but I want to just start us off with make for now. It might be something familiar. If it's not familiar, that's okay. And you might be using this in the class. You'll at least be using it for a little bit to start. So again, we can compile our software, in the command line, but again, as our project grows really big, or maybe we have hundreds or thousands of C++ files that need to be compiled, you don't want to have to type those out or remember to add them in the script. It's just kind of clunky. So we're going to do things a little bit more disciplined and use a tool to help us. We're going to be real software engineers and learn some tools here. So make is one of those build systems that's commonly used. Folks coming from Java might have used like Maven or Ant or some of those build systems, but make is the one that's been around for a long time and still is existing and developing in the C++ world. There's many other systems, but make is sort of standard. And we like make in general because it's an intelligent build system, and that it'll only recompile code that's changed since the last time we compiled it. So that makes it a little bit faster than just recompiling everything on the command line. Okay, so let's take a look at an example makefile. Again, just this might be a refresher if you haven't seen it before, or if this is your first time seeing it, we'll explain it here. So here's a makefile. They usually have a special name, make, and we use it by just typing makefile. Okay. And it'll build your software based off of different rules. So I have one rule here at line 19 and another rule here at line 25, sort of the most leftmost indented things. The indentation matters. You'll see that if you start creating your own makefiles. So just keep that in mind. What's nice about makefiles too is that we can have variables, so we can quickly change how our build works. So for instance, the compiler that we're using, CC is typically the abbreviation, =, no spaces in between. I could change this to Clang++ if I wanted to use a different C++ compiler, or call Microsoft Visual Studio's compiler here, or Intel's. Just by changing this variable here, it's easy to do that. And these are the sort of conventional names you'll see for that. You might also want to change things like the compiler flags. The standard C++ 17, maybe change it to 20. Maybe you want to add -G to give you debugging symbols, which is always a good idea, and so on. Now, after these compiler flags, there's something else here, another variable, libs, that we haven't talked about here. And I'm linking in some specific libraries. You'll see why they're going to come in handy for us. But we haven't talked about these libraries. So I'm going to leave it there a little bit on a cliffhanger for you to just take a break if you haven't already, or if you want to power through the video, you can go ahead and resume. Okay, welcome back from the break. If you're rejoining us or just powering straight through, that's also fine. Where we left off is libraries. So we're going to talk about linking in third-party libraries. This is a big part of software engineering because often you're using code that you haven't written. Maybe someone else in the company has written it. Maybe you've purchased a library to link in to do your job quicker. Okay. So often, when we're building software, we have to rely on some third-party library. The third-party library that we're going to use, so third-party means, somebody who isn't you, somebody outside of your circle. It's just what we sort of call it, third-party, has developed this specific library for us called SFML, and it's called the Simple and Fast Media Library. Okay, so someone else built this, not me, not your instructor, not anybody I know, but basically a library that allows us to do tasks that are going to be helpful for creating graphical applications. Okay, so they've built this library, but how do we actually link it in and bring it into our software? That's what I want to talk about next. And the key piece here is a tool called the linker, which is responsible for linking or gluing source code together. Okay, so when we compile source code, there's often this hidden scene that goes on for us, especially when we're using C++, but the linker is gluing all of the object files, that is the C++ files that we've compiled, together. Okay, so the linker is working there. The linker is a separate program. It's just called behind the scenes as your files get compiled, and then it glues them together. Okay, so again, in C++, every CPP file that we create is compiled behind the scenes to a .o file. Sometimes these are automatically deleted, so you don't see them, but they are compiled to a .o file. So those .o files, we say, are their own units. We'll call them translation units. And behind the scenes for us, most of the time, again, the compiler is just using this other piece of software called a linker that glues these translation units into one big one. And that's the final executable file that you see. So if you look at the sort of compilation pipeline, you have your source code files that you write. We go through this preprocessor step. That's anything that has a pound symbol in front of it. So copying in the include files and so on. Then your code finally gets compiled. Some sort of machine code gets generated. That's your assembler, where you get your .o file as the output. And then takes all those .o files together and links them into your final executable binary file. Okay, so that's a high-level overview. Maybe that's systems in a minute. One of the emphases of that course there. But that's the idea here. Okay, so the linking step, though, is one we want to take a little bit closer look at, because we're bringing in code that's not ours, and that also has to happen in the linking step. Because since we don't own the code here, we're not compiling it, our only responsibility is to just link it in to our project to say, hey, some other, friend of ours, or, a generous internet person who made this library, and we can just link it in with our project and use those functions, and that's great. Okay, so the library that we're going to be linking in is called SFML. Here's the web page. You can check it out. You'll do a little bit of an investigation today in your lab of what SFML is. I think it's a great tool. People use it for commercial applications. It's relatively stable. It has, some of its quirks, but, it's relatively stable, and we can rely on it to act bug-free in most things that we try to do. Okay, so that's just a little bit on SFML. So, go ahead and click on it, open the web page, take a look at it. It'll work on Windows, Linux, Mac. I think there are some Android and iOS builds for it that also work, which is kind of cool. So check that out. And then what we're going to want to actually do next, though, is go to the Learn page in the API documentation. So I will follow along with my slides, Learn, and then API documentation here. And you are going to get some information on SFML. As an aside, you can look at the tutorials. You can start to read these. That's totally fine. The first couple will be useful for you. I'll guide you along later. But let's just look at the API documentation. And I want to look at the different classes, right? Because we're talking about C++, we're talking about object-oriented programming. This is an object-oriented library. So we'll go to classes and see all of these wonderful classes that we have. There's a whole bunch of them. The one we care about right now is window, okay? So that's the one I'm going to show. So we have here our SFML classes. A whole bunch of them. SF is the namespace that they're in. That's why I named as I did. So all these other classes that they have created fall in the SF namespace, and we're just concerned with the window class for now. So let's just note on the tutorials. And let's say we actually want to create a window. We actually want to build a piece of software here. So I want you to take a moment to look at the window documentation here. Okay, so let's get practice using or looking at the documentation, because that's another good skill to have. We'll talk more about documentation later, but sometimes this is all you have. The documentation that's generated from a piece of source code. Sometimes you don't have tutorials, even if you work somewhere. You just have this sort of documentation. So if I'm looking at this, a few key pieces are just that in order to use the window, I need to include the window header. Okay, and if I include the window header, I get access to all of these functions here, okay, that I can publicly use here. So this is what I get for free by using this library here. Okay, and you can read more on the description here. Again, one of the reasons we're using this library is it's relatively well documented, which is nice. Okay, so we've created our window, and here's an example of just getting started here. If we want to actually write this code and get use of the Windows library we just included. It happens to be under the SFML directory /window.hpp. Okay, and that's it. As soon as we include this file here, we get all of the declarations in that window class available. Now, the key is, again, that we know these things exist, that there is a, well, let me just go to it, a window constructor. There's, maybe multiple constructors, that's fine. There's a close function, there's a create function, and so on. But we don't know how to actually do the work yet, meaning we need to link in the actual compiled files that have the definitions, okay? And those are in the form of a shared object file on Linux, dynamic link library on Windows, or dynamic library on Mac, okay? So how we do that is we have to tell during the compilation stage to link in, that's what this -l is, the SFML graphics library, -l, and then SFML-window, which contains the window function. And then we're going to just include one called system. These are the basics ones that we'll need. Okay, so this is how we get access to those C++ files that have been compiled. So we don't have the source code, but we have what they're compiled to, which is good enough for us, and we can use that. Okay, and then that'll all get glued together in our executable. Okay. Okay, so let's put it all together into a C++ project. And now I'm going to do, actually for this, a little bit of live coding. So, get ready for this. We want to build an actual screensaver. I'm going to show you a working version of screensaver, and again, walk and talk through it. And then I will, improve upon it. Okay. Okay. Now, before we begin our screensaver, little note here. Before we dive into coding, and this is going to be a little bit of a theme in the class, if you will, it's critical we plan our software just a little bit before we just dive in and start coding. Now, this is going to be a small project, so we could probably get away with diving in and just coding, but the bigger our project is, the more people involved, the more developers we have on the project, the more we have to plan it out. The planning stage is super important. So, at the very least, we need to just pick out some features that we want. So for me, I just want us to build a little screensaver so you can see the process of building a C++ project, all the different components, linking things together, and so on. So we need some sort of windowing library to draw that window. It's going to be a screensaver. We need, a ball or a shape class. I'm going to have just, one of those classic screensavers that has just a ball bouncing around to the different corners here, forever until it hits exactly, this point and bounces back and around. And, just that logic to sort of, move a circle around the screen. Okay, that's the idea. That's going to be our requirement. So with that in mind, let's watch the live session here. Okay, so I'm going to pull up here some source code to just show the screensaver as it stands, the simple screensaver. So things we talked about, again, just organizing our project, very clean. Source files, include files, bin. I can do the tree here, nice Unix command to show, again, in our bin, this is where our binary will go. In our include, we have the Windows files, and our source are our CPP files. Now I've also got a make file here, so I can open that up, and you'll see it's the same one shown from the class. Okay, so I'm going to have my libraries linked in from the third party, my include directory to bring in all the header files, and then where the binary will be generated. Okay, so we're going to use our compiler G++. You can just see it here. Our flags here, I'm going to turn one more on, -G for debugging in case we run into any problems. And then maybe another one, -W all. This gives me all the warnings. These are some good ones to turn on. I'm just doing it to show you what's possible. And then we're using our source code, and I want to compile the star here as a wildcard character for compiling anything that's in our source directory, all these C++ files. That's what our compiler is going to do. And then we include all of our header files, so where to look for those in the include directory. The output is going to be whatever our binary file is named. It's just called app here for application. And then any third-party libraries that we need to link in as well. So the SFML libraries here. Again, the -L is just a flag that's sent into the compiler. This is the actual name, SFML graphics for one of the libraries, FFML, window here. Okay, and then there's another rule for cleaning the binary to get rid of it. Okay, so with that, I can run make. I did get some warnings. That's okay. These are good to know about. But if I do tree again, I will see the application has been built. So if I do /bin/app, I will get a little screensaver application here with a ball that bounces around on each corner, forever. And this could be a basic screensaver, but if I hit exit, it will terminate the program here. Okay, so that's all very exciting. Let's actually look at the code here. I'm going to split my window. I'll keep the code on the top and recompile at the bottom where necessary. Now, let me actually back out a directory and go to our screensaver. This is a copy of that same file, and actually start doing some refactoring as I show you the source code. Let's start with the main function here in source. Okay. What I've got here is a main function. So I always look for the entry point of the program here and the basic logic. So I can kind of read through this. We create a window, set the frame rate. We're going to create a circle, And then forever, since this is a graphics program, it's a screensaver, it's just going to run forever, we tackle this code here. So I clear our window just to make a black background. We listen for any events that could happen, such as if the escape key is pressed, which would then terminate our program. So then we just close our window and terminate our application. Otherwise, if that doesn't happen, we update our window, we update our circle object that's flying around, and we draw the circle on the window and then display all of the objects on our window. Okay, so this is what we've got. Now you might have noticed there's a bunch of other stuff up here. There's a class here, some constants here, and this is what I actually want to get to refactoring. But let me show the rest of the code here, just so we can see everything, and then we'll refactor. The window class, which I included before, is just included here. We're not actually doing much work there. And then if I go into the include folder, I have the window, which has our interface. Okay. Now let's actually clean this up a little bit. Okay, so I'm going to open up Vim and the window. Let me just open up the main file, because what I want to refactor here is this class here. This should really be in its own file. Occasionally you'll see this in small projects, but we want to move this out here. Right? Our main should really only have that main function or logic, no declarations here. So what I'm going to do is create another file. So I'm going to split my window here. And in the include directory, create one called shape.hpp. Okay, and then paste in this class here. So let me add my header guards, if not defined, circle H, define circle H, and then at the very end, I will end if here. Okay, so that's now saved. And I actually want to name this something a little bit better. Let me just actually name it circle. So I'll go to the include, see the files I have, and name it circle.hpp. I like to match the actual name of the class or how it's instantiated. Okay. So let's open that up. And again, this is on our left side here, on this side. Just our interface, it's the header file. So we need to actually remove a lot of this, these functions here, or the function definitions. So what that means is I'll open up another file here, source, and we need a circle C++ file here. Okay. So let's open that up. Whoops. Let's just split our window. And we have a C++ file here, and we include it. Okay. Now let me just indent this here. Okay. So what I want to do is I need to include, what rename this circle HPP, because we need to know about in our C++ file again the actual definitions here. So again, this file should just have the definitions. So I'm going to clean this up and remove all of our interface here. Let me get rid of this. All of our curly braces, okay? So I'm going to delete these. And I just need, this is just called the function signature. This is our member function, and that's all we need there. Let me get rid of all the logic here. All these curly braces. I can do this in a bunch of different ways, but this is how we have it here. Okay, so here's my constructor, and typically I'll add the documentation in the header file destructor, because this is what a user would look at or see so they know how to use it. Updates the circle's position bounded by x max and y max, and this is draws the actual circle in the window. Okay. Note passes by reference. So this is a new C++ thing. We see the ampersand here. So this is just passing a reference to that window object here. So we'll see that in a moment. Then I have all of my members here. I like to prefix them with m underscore so that I know that they're member variables of a particular class. That's a stylistic thing that I generally try to follow here. And I might make it a little bit nicer here. So again, just a little bit of refactoring here, just so you can see what, in my opinion, nice C++ code looks like here. Okay, and usually I would have maybe a purpose of the class, how to use, or a usage example. We'll talk about this a little bit more as we dive into it, but that's the basic refactoring, okay, on our interface here. Now we're not quite done because we need to appropriately, we've included these definitions of functions here, but we need to set the scope. Okay, so these all belong to the circle class, so that's where we'll find these functions here. So I need to actually set those up by setting the appropriate scope and for draw, and then I am good there. And then I need to open up one more Vim window here, and it's in source and the main file, and we are making use of the circle. Okay, so here we want to include circle. Let me get it at lowercase. We might have wanted to do it uppercase, but that's okay. Okay, so let me now try to reuse my make file and see if it works. Oh, I got a few errors here. Totally fine. Looks like I'm missing a semicolon, line 26. And I like to, in general in C++, I like to, whoops, I lost my window. Let me bring it back. So here it is. But in general, I like to work sort of top to bottom if I've made any errors here. So we'll see there's quite a bit. So what did I forget to do? Well, one other one I saw is I forgot to, I've declared the destructor here, but I need to define it. So I didn't do that in this other window. Or I did, but it's not in the right scope. So where do I find this function? It's in the circle class, okay? And let me go ahead and just indent these properly here. And as I fix one thing, I try to remake again, okay? And then I go up and I see, oh, there's all these other errors here. Some different things that we see are going on wrong. Again, this is part of the refactoring. This is why we plan ahead and just work really small steps at a time. So I'm noticing a lot of different errors about like this render window doesn't exist, or these things. So because I'm using SFML functions in my header class, I need to also include those here. Okay, so I need to include SFML window.hpp and include SFML graphics.hpp. That way, if this file here, this C++ file, or this header file, whichever one of these two happens to get compiled before this main CPP, the appropriate interfaces that are being used here, like the render window or the circle shape found in graphics, will also be included. So again, one change, saved my code, and we'll also remake, and we're getting fewer and fewer errors, which is good here. Okay, so now we're just getting some errors about expecting curly braces. So this looks like some curly brace errors here. Let me clean up what I was doing here. And I don't need to set up the constructor there. I'll talk a little bit more about some of these things in a moment. We are almost compiled here, which is great. And let me get rid of this explicit mark here. I think I'll need to get rid of it in both places for now. That's okay. Explicit says this must be a bool or float and doesn't cast anything. Let me just get rid of that right now, just to make sure that our code's compiling during this refactoring. and run our application, and it's still the same one. Okay. All right, so a few pieces here that are going to be new. The constructor here, where I'm setting up, it's a function that takes in a special function that's first called to construct our circle when we first create it. But it's taken in 3 arguments here, up, left, and radius. And something in C++ you can do, this is sort of the style here, is to do what's called an initializer list and just very intentionally, I will say, set up the member variable. So those were the things m underscore to the argument value here. M underscore left is just whatever the value is here left. You could otherwise just do something like m underscore up equals up, but it just saves you from doing that. It's a little bit better style. There might be some performance implications as well. Okay. But here's our interface. Here's the destructor. We're not allocating any memory, but here's where we would do things like delete if we needed to, or if it's an array, delete with the brackets, and so on. The logic of this program is that if our object's moving up, we move it by 1 unit up. So pixels, 0s towards the top, whatever our resolution is at the bottom, and so on. If we're moving left, we move 1 pixel left. If we move right, otherwise we go here. And then we change the bounds of where we're moving, left or right, by just if we reach our sort of limit. So if we're at the 0th x position, which is all the way on the left side of my screen, then we're not going to move left anymore. So that's false. We want to move to the right. Okay, so that's the logic of the program. So we're calling that and then setting our shape's position. Okay, and then the draw function, again, a little bit of weird stuff since we're passing by reference. Let me just, again, show this, how this is done by moving here and where the actual draw is. Here's our actual call to draw from our circle class. And we're passing in window by reference. So this is the window that we have created here. It's sort of like a pointer, it's passing in the actual window here that we've created, and then saying very explicitly to draw to that one. Okay, so again, that's when you're passing by reference. It's not making a copy here, it's the actual window. And then you can use all of the render window functions here. Okay, you can think of this as just an alias when you see pass by reference. Okay, so let's spice this up a little bit. My argument is, if I make my font a little bit smaller, just so you can see the whole program in sort of one screen here. This is a little bit cleaner because I just have to worry about this side and then creating circle objects, and then all of the work about updating and the logic and stuff is just in these individual functions here. Okay, so if I want to do something kind of neat, maybe make our screensaver more interesting, I just want to show you how I could create multiple of those circles here. Okay, so I'll try to do it as fast as possible. Okay, so what I'm going to do is just look up some documentation for randomizing where our circle starts. Okay, so I'm going to use the rand function. This is on the c++.com reference, and it looks like it's defined in C standard library here. Okay, or I can use part of this example. This is using some sort of C code. If I don't understand it, I can actually edit and run it, which is kind of cool. So just a little resource you can see there. But let's go ahead and use these functions here. Open up my code, and I want to now randomize the starting position of my circle here. I like to include the functionality where I use it. Oops. So let's paste in those libraries here. So we have that functionality in our, and because again, I'm working in the header file here, I paste in these libraries. They're accessible in my CPP because I'm including the circle HPP here. So this is just a copy and paste of everything in this file, everything on this side here. Okay, so the srand function, I'm going to set a random seed here, And then I want to set some random values here of something reasonable. Let's say within 100 here. So rand within 100 plus 1, and rand within 100 plus 1. So that's just going to make my x and y position random. I like to build often to see if it works, and run often to see if we get different results, if it seems like it's moving randomly. Okay, and then the direction itself should probably be randomized too, this sort of up and left function and so on, but you know, let's just increase this by a little bit here. And then rebuild and remake here. So you can see we're getting, you know, some more interesting results here. Okay, so what else that we want to do is, actually let me just randomize the up and the left. So that means a change to our interface here. So we're just going to change the radius. In fact, let's just get rid of all of the interface here, just to make things more interesting for our screensaver. Now we have two choices where I can either do what I'm doing now, or maybe I do want to preserve this interface and I can create a second constructor here. Okay, so let's just go ahead and do that. And based off of which constructor I'm doing, I can construct objects in a different way. Okay, so this is our constructor. Let me just fix the comments here because I'm going to upload this so that you can look at it. And I'll just have a second circle constructor here. Now, that's going to require me to copy this code here and create our second constructor here. Okay, and paste it in. And then this time, the things that we didn't set up, m up is going to be a random value between 0 and 1. So I believe this will do the trick, and it's an integer, so I want to make sure I cast it to an integer. Rand of 1, and I think this will work here. And the left, oops, the left side here. And then finally, we want to do the same thing for radius. Okay, but let's randomize our radius to be between 10. Okay, so and plus 1. These ones, let's see, we want to do between 1 and 0, so I need to add mod by 1 and add 1 here. So I think that'll do the trick here. Okay, so now let's actually create a second circle here. Circle, my second circle. And we're not going to use the previous constructor, so it'll call this function appropriately. And now what I want to do is the same thing and create each of my circles here. Name them my second circle and my second circle here. Okay, let's try to make. And looks almost good, except for I might have made a tiny spelling mistake here. Which I think the constructor just needs to be, oh, these empty parentheses can be removed. There we go. Make. Okay, perfect. Now let's try to run it and see what happens now. And it looks like I got a tiny little circle here. Let's run it a couple times. And yeah, what do you know? It's actually doing some kind of random stuff. These are moving in opposite directions. One's going up, one's going down. Seems like it's working. Maybe there's, you know, the randomization could be a little bit better here. So let's move our seed here. And there we go. And just run it a few times. We'll talk a little bit more about testing, but this looks pretty good to me. Okay, great. They're moving in opposite directions, or it looks like it's randomized. Okay, so now the next question is, you know, this isn't a really interesting screensaver unless we can have lots of circles here. So I want to introduce different libraries. So we have the third-party library here. This is our SFML library. We have our classes or our includes, that's right here. And then we also have the C++ standard template library. So you're going to do a little bit of investigation on this in your lab, but we want a data structure where I can just say, hey, let's just make a bunch of circles, populate them, and then I won't have to create all of them at once here. One of the key data structures that we use is something called a vector. It's a dynamic array. So let's take advantage of that. So I'm going to again refactor, but this time in the standard template library namespace, so std for standard in that scope, I'm going to create a vector, and it needs a type. And ours is going to be circle, and this is going to be called the circles vector here. Okay. So now what I'm going to do is just in a loop for int I equals 0, I less than 10, I plus plus, create a bunch of circles in this loop here. Okay, I'm going to copy one. I'm going to get rid of our first circle there. Just call these temp, and then I'm going to push these as I allocate them into this vector structure. Okay, so I'm going to create 10 here. And then now in my actual draw code, I'm going to say for int I equals 0, I less than 10, I plus plus. I want to update and draw these circles. Okay, this is the work that I want to do. So I can get rid of this code. Now these are part of our circles vector. Circles at a particular index. I want to update so that it only it's constrained by 640 by 480 circles I draw and for the window. Okay, so let's go ahead and see if this builds. Always great feeling when it builds the first time, and actually run our application and see if it gets more interesting. Something weird happened here. And it looks like there's two problems in my code that I can notice. One is, well, I guess the range of these rands is not quite correct. This would give me a value between 0 and 1, so that's what I want here. But the second I've got to be really careful about is my random number. When I was generating it, I'm constantly seeding it or saying, hey, generate from a special seed from 0 in the system time. So I don't want to do that in this class. I want to actually just do this in my main class. Set random number generator here. So let's do that. Let's also get rid of this rand here. And just in case, let's include C time, which is where the random number generator is here. Okay, so let me clear this. I'll use my make clean rule to ensure my binary is removed. I like to do that every once in a while just to make sure it's absolutely gone. Run the app, and then cool, we're getting something more interesting here to look at. Now, there's still more refactorings that can be done because I don't quite like how this code is in the sense of I have to remember some of these magic numbers here. Yeah, this one's interesting. Let's just make it 100. Every time I change that, I need to also change this value here. But again, through the power of object-oriented programming, we can use circles, and there's actually a length function here, or size, that will tell us the size of this collection. So I don't think it's length, that's just a member variable here. Whoops, I guess it is size. Size, and that way we don't have to remember 100 here. So I'm just going to make it and do a little experiment here, and this is much more interesting. Now, likewise, you see there's still something a little bit wrong. Everything's just starts off in this sort of group here, but again, we can improve that. I'll leave that for you folks to explore the window get width and get height, which we could put in here. You might also explore other things like changing the colors of the circles or the speeds, and then you sort of start getting a more interesting visualization here. But that's where I want to end us for now for this live coding session. So that's a little bit about how I developed. That's a little bit about using object-oriented programming to make our lives easier. We don't have to remember collection sizes. We can just sort of put everything in a vector. So you'll learn a little bit about vector classes and so on. So this is pretty cool. Here's your CS5500 screensaver to start. So let me run us back to the slides and wrap up this slideshow here. From our live session. So here was the documentation on the RAND. So I just looked at this again to be a little bit careful. And for the window class, again, you might look at things like the width, member functions. Usually I'm just doing Control F to sort of quickly search these things. And I believe there should be a function here for getting the width, and we're actually in the render window class here. So if I search and search and search and search, let's see if I can help you out here. Usually they start with get and the width. Looks like it's just something we'll have to save somewhere else. So one last thing, I have those values saved here as expressions that'll be evaluated there in globals. We'll talk about how to get rid of globals when we talk about design patterns. Okay, anyway, back to the slideshow from our live session. So do make sure to complete your in-class activity that's been set up for you in a module. They're worth part of your grade, and for the lab. So the last portion here, and of course, Wednesday we'll have more in-depth question. Do a git pull from your mono repo just to make sure that you have lab 2. Assignment 2 is also ready to go a little bit early for you. But just a little bit about what the lab's about. It's really about API design in languages. So just a few notes here. What's an API? SFML is one, but it's an application programming interface. And sometimes folks say abstract programming interface, but it's usually a library of code. So we saw SFML in this example. I briefly introduced C++ standard template library and so on. So you're going to look at some of those functions from these libraries in your lab and comment on them. Okay, so I want you just looking at them. You can try the example today if you like, but in general, good APIs, and you'll be the one to decide this, make our lives easier. So here's a graphics API. It's a C-based API. Graphics students will be familiar with it, but the SDL library, and it has a bunch of functions available for us. We don't care how they work. We just care that, this function load BMP can help us load an image. It's got a good name here. It's got its action, sort of a verb here that tells us what it's doing. We can see the return value. That's pretty good for us. That tells us what we need, okay? But we can do better and have cleaner APIs. Object-oriented programming can often help us with that. C++, helps us with some of this abstraction. There's a reason sometimes to use one or the other when it comes to performance, but I like this texture, load from file, and here is how it works. And just chooses the right file. It's not load BMP, it's just load from file, and then it'll figure out from the arguments if it's a PNG, a BMP, etc. Okay. So good APIs have this sort of design. They're very explicit. You don't have to guess what the functions are doing, and that you can also test them. Okay, so that's all I got for this lecture. Hopefully everybody's doing well. We will talk to you tomorrow, or rather, in our lecture and lab office hour sessions.